everybody, it's Miss Dibadol. Just kidding, it's Mr. Athide. Psych, gotcha. We are going to be using rate of change to determine the type of relation. That's right, I can do math too. So a bit of a warm-up for you to do, and I'll take it through it in a second, but you're going to try it first. There's a couple of patterns here. You are going to compare them. You are going to see how they are alike, how they are different. Write down what you're observing, what you're noting. As a challenge, see if you can write an equation that determines the value of each term. So if these are the values up here, based on its position P in the list. So if we're talking about position 1, position 2, position 3, position 4, etc., etc. How are those two things linked? It's a bit of a challenge because you haven't really gone through that yet. You will in a future lesson. But for now, just see what you can do. And while you are making all these considerations, as you're seeing how they're alike, how they're different, all that jazz, as we've noted that there's a position 1 and 2 and 3 and 4 and so on and so forth, don't forget to consider the initial value or the zeroth term in that whole sequence. So give it a go. Pause this video for, I don't know, like a few minutes. Talk to people around you about this specifically. See what you come up with, compare ideas, and then resume this video. Wow, that was a great pause. I hope you had lots of great discussions. Now it's my turn. There's stuff I see when I look at this first pattern, the 3, 5, 7, 9, etc., etc. It looks like as we go from term to term, we are adding 2. So we add 2 to get from 3 to 5. We add 2 to get from 5 to 7. We add 2 to get from 7 to 9. And if we're making that consideration for what the zeroth value is, we go the other way. And if we're not adding 2, if we're doing the opposite of that, we must be subtracting 2 instead, which means that our zeroth term must be 2 less than 3. So that must be, whoa, that ended up weird. Must be 1. And again, that's our so-called zeroth term. So that's in like position 0. There's position 1, position 2, position 3, position 4. When I look at this other one, 2, 4, 8, 16, we could say that like it goes up by 2 and then goes up by 4 and then goes up by 8 and so on and so forth. So there's a pattern with how much they're going up by each time. But for me personally, the thing I most directly see is to get from term to term, I am multiplying by 2. So I take 2 times 2, that's 4. If I take that and multiply it by 2, I get 8. And if I take that and multiply it by 2, whoops, that's a plus. I know the difference. Totally. Then I get 16. And I could continue this pattern to get each next number in there. But I've got those ones in there. I've got term number 1, term number 2, term number 3, term number 4. And we still want to make that consideration of what's the zeroth term. So we want to go the other way. If we are undoing multiplication by 2, that would be then division by 2. Which means my zeroth term is going to be 2 divided by 2, so it's 1. And then a comma to separate things. Cool. So in comparing these, there's not a ton that they have alike, but the one thing they do for sure have in common is their initial value, or that zeroth term. So they both have the same initial value, or what we call the 0th term. Also, if you plan on doing computer science at some point in your life, getting used to starting with an index of 0, super handy. Take it from a computer science nerd. That would be me. I'm the nerd. How they are different. I mean, for starters, they use different numbers and such. But in terms of the procedure to get each next number in line, we can see something pretty clear. So for one of them, for the first pattern, we're adding 2 to get to each next term. So we add 2 to get to each next term. So key is adding. Whoa, that underline was questionable. Add. Nailed it. Whereas for the other one, even though 2 is involved, we're not adding. So for the second pattern, we multiply by 2. So one of them we were adding the whole time, one of them we were multiplying the whole time. Always by the same number, so adding 2, adding 2, adding 2, or multiplying by the same number, multiply by 2, multiply by 2, multiply by 2. So there's a constancy in there, and then the operation itself within a certain pattern stayed constant. And the challenge part, again, no worries if you didn't get this, but writing an equation that determines the value of the term, so if this value of the term is v and the position number at the bottom is p, there's a link between the two of them. More specifically, let me just erase this, you don't need that. For the first one, the value is 2 times p plus 1. And you can check it out, right? Like at position 1, this 1 times 2 plus 1 is 3. 2 times 2 plus 1 is 5. 3 times 2 plus 1 is 7. 4 times 2 plus 1 is 9. So you can see it in action there. You can always test out whatever you think a pattern is. And similarly, we could test out things for the second pattern, but the result is that the value is 2 to the power of p. So again, checking it out, if Joanna, first term should be 2 to the power of 1. 2 to the power of 1 is 2. Second term should be 2 to the power of 2, and 2 to the power of 2 is 4. The next term should be 2 to the power of 3, which is indeed 8. So this is following along with that pattern that's been established, if you want to check it. Great way to check it. What we really want to focus in on is a pattern like this one, where we were adding something each next time, because that is something that happens when we look at a linear relation. So some relations are linear, and there's a whole bunch of types of relations that are not. So with these relations that have us always adding the same amount to get from one term to the next, or a constant amount, that gives us something that is linear. So a linear relation, it's a relationship between two variables, but the rate of change has to be, whoa, how many times do I have to erase? But it has to be constant. So as one variable changes, that amount it changes by has to be same as the other variable is changing by some constant amount. That's what makes something a linear relation. And we call it a linear relation because of what its graph looks like. The graph of a linear relation is going to give you a straight line. And just to be clear, we're talking about images like these. Those are linear relations. If you have a bend in it of some sort, even though the segments themselves might be linear, overall it's not fully giving you a linear relation, so no county. Just a single straight line like these cases. That's giving us a linear relation. Eraser, help me. Nailed it, first try. So rate of change, no matter where you look on the graph, it's going to be same. It's like walking up a hill and you're always going up by the same amount. The steepness doesn't change. If the steepness changes, well then your rate of change has changed and you're no longer dealing with the linear relation. A real life example, other than walking up a hill, you could talk about a child who earns $1 for each chore they complete. There's a rate of change, it's $1 per chore, or for each chore. And the graph would be a straight line. If it's nonlinear, then these conditions aren't being met. So that's a relationship where the rate of change is not constant. Whoa. Not constant. And as a result, the graph of a nonlinear relation will not form a single straight line. There's some examples over here. That's not every single nonlinear relation that exists. There's infinitely many, but that's some. And we could see, like, if somebody was going on this roller coaster, they would go wee down the hill, and all of a sudden, whoa, they're going up. They have changed their directionality, the steepness changes. There's not a constancy there. Where's my eraser at? Nailed it again. Oh, let's erase the person too. Be gone, person. So the rate of change, just like that person on that amazing roller coaster, that rate of change, it itself changes as you move along the graph. Sometimes you're moving up slowly, sometimes you might be moving up quickly, or moving up versus moving down, or moving down slowly, moving down quickly. So example in real life, it could be the distance traveled by a car that speeds up over time. The rate of change of that distance is its speed. And since the speed is changing, the rate of change is changing as the car goes faster and faster. So again, linear relations, we're talking about straight lines. You want to identify a linear relation from a graph? Just check if the graph forms a single straight line. If it does, then we've got something linear. If it does not, then we have something non-linear. For example, this first graph over here, we can see that that's all curvy. That's one roller coaster right there. So that must be non-linear. Whereas this next giraffe over here is just a straight line segment. Maybe it goes on forever, I don't know. But it's for sure just a straight line. And because it's just a straight line, that must be linear. So pictorially, super easy to spot. It's like, just look at it. Is it just a line? And again, line in math is specifically a straight line, not a curvy-wurvy, what we might call in other aspects a line. From an ordered list, we want to look at what happens as we go from term to term. Again, we always want to be adding a constant amount, and that goes back to this definition over here. Changing by a constant amount. Here we've got a bunch of terms. To get from 1 to 4, we have to add something. We have to add 3. to get from 4 to 7, if this is linear, then we better be adding 3 again. And sure enough, if we take 4 and we add 3, we get 7. So far, so good. To be absolutely certain, though, it does need to work, not just for the first few terms, but all of the terms. So we quickly check over that as well. We should be able to do this same change. Take 7, add 3, and we do get 10. So this is all great, and we are happy. So that again tells us that this must be a linear relation. Linear. Go ahead, do a quick check on the next one. Take a solid 37 seconds for it. You know, you don't even need to pause the video, I'll just time it out. I lost count somewhere along the way. I don't know how to count to 37. It's way too big a number. But let's check this out. So if it's linear, we must be adding the same thing to get from term to term. And to get from 1 to 3, we have to add 2. So, as long as it's the same throughout, we should be A-okay. To go from 3 to 5, we are adding 2. Wow, I guess this thing's just straight up linear. What a great conclusion to draw. Just kidding. Don't forget to check the last term as well. And to get from 5 to 8, we're not adding 2. We're adding 3. And because that's different, this thing is non-linear. So that's ordered list. And you can also note we're going up by an index of 1 each time, right? This term 1, term 2, term 3, term 4. So as these top numbers are, or as the numbers themselves are changing, the values, their positions are also changing by a constant amount. They're always changing by 1. And same with the other one. We've got, the first term, the second term, the third term, the fourth term. So as these as the values themselves are changing by a constant amount, the positions are also changing by a constant amount. From a table of values, we can kind of operate similarly. It's just instead of counting in like 1, 2, 3, 4, we might have different values put in there for x. When we want to check if a table of values does give us a linear relation, we have to check that both of these are changing by constants, not just one of the columns and not just some things in the columns. So we have to, again, check both. The moment we find a rate of change that's different, we can immediately say that we have something that is non-linear. But if we are getting a common rate of change, same rate of change throughout, we have to keep checking to make sure it works for the entire set of numbers, not just for a few, not just for 1 or 2 or 3, but for every single row. And if that's the case, then yeah, super awesome. It's kind of like if I went around and said, oh, everyone I know has brown hair. And I started looking at a brown-haired person, and then I saw another brown-haired person and a brown-haired person. I'd be like, I can't just conclude there. I still have to, I may have said it was everyone. So I have to look at everyone. But if I say, oh, everyone I know has brown hair, and I see someone with brown hair, and then I turn and I see someone with blonde hair, it's like, okay, I can stop checking. My claim is false. But let's try that out here. We can look at each of these columns. So the x values, to go from 0 to 2, we have to add 2. To go from 27 to 22, we have to subtract 5. The rate of change here is how much y changed divided by how much x changed. So the rate of change is negative 5/2. We check the next one. To go from 2 to 4 for x, that requires us to add 2. To go from 22 to 17, we subtract 5. And, well, again, we've gotten a rate of change of negative 5/2. So far, so good. The rate of change is the same, but we're not done. It has to work for everything. Continuing along. To get from 4 to 6, we add 2. To get from 17 to 12, we subtract 5. So once again, our rate of change is negative 5/2. And finally, to go from 6 to 8, we're adding 2. To go from 12 to 7, whoops, wrong color. We are subtracting 5, so the rate of change is still negative 5/2. With the rate of change being constant, we know for sure this relation must be linear. It's worth noting that they don't necessarily have to go up by same amounts. We just need the rate of change to be constant. Like, I could add another row to this. I could say, I don't know, let's just put in 12 and a y value of negative 3. And we could double check what that rate of change is, because to go there, we'd have to add 4 for the x value. And for y, that's subtraction of 10. And the rate of change, sure, it's negative 10/4, but that reduces to negative 5/2. So still same rate of change. That was just a little aside to say, like, it doesn't have to be constant values that we're changing by, as long as the rate of change itself is constant. In any case, our conclusion here is that this is linear. And that's because there is a constant rate of change. Quick, I dare you to try the next one. Give it a solid 2 minutes. Pause the video, resume, see what you get. Go. Good pausing. You did great with the whole pausing thing. We're resuming. So I'm going to go ahead and show you what I got. Let's see. We added 1 for x, and then we added 2 for x, and then we added 4 for x, and then we added 2 for x. Cool. For y, we added 1, we added 2, we added 5, we added 3. All very lovely numbers. Let's check those rates of change. First one. Y went up by 1, x went up by 1. Our rate of change is 1/1, which is just 1. Cool. And the next one, we've got 2/2, which is also 1. Oh, awesome. I guess this whole thing's linear, hey? Psych, watch out, because the next rate of change is 5/4. And if you want, you could rewrite that as 1 1/4. But regardless, it is not 1. And because we don't have a constant rate of change, constant rate of change, this relation must be non-linear. I don't even have to check the last one because the rule's already been broken. Can't get more broken than that. We've got some examples. We've got some patterns here. We want to fill in missing values and state if the relation is linear or non-linear based on what we can find. As we look at example A, it's worth noting we're jumping from term to term, right? So we've got our first term, our second term, our third term, our fourth term, fifth term, sixth term, right? Those are all in there. And as we perform these jumps, there's a single jump here where we add 4. If this is linear, we should be able to perform that jump again to get to position 3, and then perform that jump again to get to position 4 and end up at this value of 20. If that works out, awesome possum, this thing's linear. If it doesn't, then it must not have been linear at all. But let's just check it out. So 12 plus 4 gives us 16 in that spot. And then 16 plus 4, oh, that does give us 20. So, cool. Linear so far. Not quite done. We still need to make sure that that continues as we go along. So, plus 4 gives us 24 in position 5. And we should be able to add 4 again, and sure enough, 24 plus 4 is 28. So we're all good in the hood here. This must be linear. And that's because the values change by a constant amount. Take a moment, do some pattern detection in these other two examples. See if you can figure out how we're getting from term to term. Maybe it's linear, maybe it's not. Suppose things, guess things, try them out, test them out. See what happens, and then draw a conclusion. Is it linear or is it not? Spend a solid 3 minutes. Pause this video, give it a try, and then resume. Hi, welcome back. Lovely to see you. Taking a look at this example, again, hoping that it's linear, but we'll see what happens. Term to term, you will have discovered that we subtract 6. Cool. So if it is linear, we should be able to keep subtracting 6. 28 minus 6 is 22. And then hopefully that keeps working. 22 minus 6 is 16. So, phew, sigh of relief there. 16 minus 6 is 10. And 10 minus 6 is 4. So this works out to be linear. Because again, the values change by a constant amount. And looking at the last one, all right, we're on a real linear streak. Let's keep it going. 4 to 12, that's us adding 8. And then 12 to 36, that's us adding 8. Oh, that's not 8 at all. My goodness, that's 24. So this is right away just non-linear. Wow, nice try, Miss T. She tried to fool us. Not today. Non-linear. And that is because the values... Oh, sorry, that writing is gross. Let me just adjust that. So this is non-linear. And that's because the values, sorry, messy writing again. Do not change by a constant amount. I'm not really done the question. It did say we were supposed to fill in the missing values, so we do need to detect what's going on there. Personally, if I see it's not a constant addition that's happening, I'm gonna see if it's multiplication. So just examining it, 4 to 12, I'd have to multiply by 3, and hopefully that works for the other terms in here. And 12 times 3 does give me 36. Seems good. 36 times 3 does give me 108. So, okay, it's some other kind of relation. It's an exponential relation. But you might not need to know that until like grade 12, who knows. I can fill in the rest of the colors here. Or the rest of the numbers here. Again, just multiplying by 3 the whole way. 108 times 3, 100 times 3 is 300. And then 8 times 3 is 24. 24 times 3 is 72, and 300 times 3 is 900. So there's that all filled out. And then finally, we have this linear relation that Zenon had. Zenon was walking home with this newly found linear relation. Mid-walk, it started to rain. And the data some of it was no longer legible. We have to fill in the missing values for poor Zenon since he didn't put everything in a waterproof backpack. Rookie mistake. But we know it's linear, which means our rate of change from row to row has to be constant. Now, worth noting is to get from negative 13 to negative 6, we have to add 7. And to get from negative 20 to negative 13, we also have to add 7. Since negative 34 and negative 20 are 14 apart, that must have also come from a couple of additions of 7. So that allows us to fill in this one blank here. Negative 34 plus 7 is negative 27. But what goes here? Again, we need this to be linear. We need a constant rate of change. But we don't know what it is. Like, are we adding, 6 each time? Are we adding 5 each time? Are we adding 12 each time? Like, I don't know what we're adding here. And my addition sign looks like a T. That is so sad. There's a way for us to figure it out. We can't just guess and check, especially because this does say determine. Determine means we need to show our process, show what happened. But we are noting again, don't forget, there is a constant rate of change. So if one of these columns is going up by a constant amount, this other column must also be going up by a constant amount. Sure, we don't know what that is yet. That's fine. Call it X. Don't know what it is. A good default unknown is X. Oops, I should say that we are adding this X. And then we're going to add this X again. And then we're going to add this X again. And then we're going to add this X again. And then boom, we've gone from 2 to 42. And when we really put all that together, what we're saying is if we take 2, we add X, we add X, we add X, and we add X again, we get 42. There's a way better way of writing that, because that is 2 plus 4x. And that equation we could solve all day. I'm going to subtract 2 from both sides. So now I know that 4x is 40. And I'm going to divide both sides as well. divide by 4 on the left, and for balance, divide on the right as well. And that tells us that x is 10. And now we can fill in all these values. So 2 plus 10 is 12. 12 plus 10 is 22. 22 plus 10 is 32. And just finally checking that my answer actually makes sense. Make sure it works to the end as well. 32 plus 10 gives us the 42. So we must have done something correctly. So that's kind of it, that's all. Make sure you do all your practice work. I hope you've enjoyed listening to my soothing baritone for mathematics. And remember, everyone who does math is cool. I'm an adult, so you know it's true. The